kulms.korea.ac.kr, right? Okay. So this is called the Blackboard website. And, there I will post class material or slides and homework and so on. Okay, so the goal of this course is to study the probability and statistics, right? And so those basic concepts include those sample space, event, conditional probability, and joint probability, and marginal probability distribution, and independence, like just independence, as well as the conditional independence, and also this Bayes rule that you will hear at least 1,000 times. And then we will try to study various continuous and discrete probability distributions, including, so you guys know the normal distribution and uniform distribution, but there are so many other distributions that might be good to study, including a beta distribution, Cauchy distribution, and also multinomial distribution, binomial distribution, and things like that. So honestly, I'm not familiar with all these, so I will also study as much as possible so that I can teach you guys well. Okay, and then probably the last part of the course will be focusing on this confidence intervals and hypothesis testing. So like, so is it really true that the men and women have a different heights? Okay, on average. I mean, we should be able to answer such types of questions from a statistical sense, okay? So those types of hypothesis testing, and also at the very last, we will touch upon this so famous topic of linear regression from the probability perspective. So yeah, from the linear regression, I mean linear algebra perspective, we learned about the least square and then also the linear regression based on this least square techniques. But those exact same techniques can be also described by just modeling the errors between the actual data and our linear model. I mean those difference between these two, actual and real world data and models data. Those errors can be formulated as also the probability, some kind of samples from the probability distribution. So, okay, so that is briefly what we will learn from this in this course. And this is the textbook. So, Probability and Statistics for Engineers and Scientists, in 9th edition by Ronald Walpole. And this book, I heard that this book is not available yet at the bookstore. But the publisher called me saying this book will be available by the mid September. So you should be able to find this book in the bookstore in within 2 weeks. Okay. Yeah. So yeah. I know it sounds silly, but you know, this book, yeah, it's kind of off the record, but this book can be easily found online as a PDF or this kind of online version. So you can easily obtain those PDF file, and then I believe we will have no problem in studying this course at the early stage of this course. Okay, and especially. The first part of the contents that we will learn is quite boring because we learned too much in our high school. So it's yeah, in that sense, it's kind of similar to linear algebra or the previous mathematics course in this semester. I mean, in the previous semester. So the first part looks quite easy, and it seems like we learned all of them already in high school. But suddenly there should be some jump. I mean, unless you have like a solid background or like really strong like knowledge about all these fundamental basics, yeah. If you don't have that, and then this course will be suddenly become a nightmare. Okay, so yeah, just. Yeah, it would be good to just be prepared for it. So, yeah, please keep like paying attention about this course. Okay, here's the course schedule. Okay, so the most important part, which is about this grading policy. So if you have taken my previous course about the linear algebra, and then it will be just done in a quite similar style. We have those about 5 or 6 number of homework assignments where you basically have to, it's basically problem solving. So I will pick up those problems from the book, and then you have to solve by hand or by typing in the computer, and then submit those answers. And then we will have, so this is a good news. So earlier we had 2 midterm exams, but now I decided to only have 1 exam. One midterm exam. Okay, so we'll see, whether this is better. In terms of your kind of course achievements or not. But anyways, I decided to take a shot on this, just a regular kind of style of 1 midterm and 1 final. And also the class participation is taking up about 5%. And so from my I'm gonna just tell you my earlier experience. So I'll be the grader, right? I'll be assigning your final letter grades ranging from A+, A0, B+, and so on, right? But often people or some of the students are really around the borderline, right? So so if I just rank all of you based on this quantified scores of homework and exams, and then there should be no kind of a possibility of adjusting among these students. But from those class participation, I often remember. Of course, I often remember those students that quite ask the questions quite often, and then a few of the students got a higher grade at the end in terms of a letter grade due to this class participation. So nobody will know. Who will be around that borderline where this class participation will really play an important role. Okay, and then the attendance. So so this is definitely a probability and statistics course, and so I'll actually perform subset of you guys to check the attendance. So it will be exact same as the previous class that I had. So if you guys are familiar with such kind of attendance checking style, and then that will be exactly the same. So I will just maybe call 20 of you guys at a time at every class, and then once a student sampled that way is missing the class, and then I will give a higher weight in the next time. So I will basically increase more probability to get sampled for that student who missed the class. Okay, and then as you guys see, the first 3 items are summing up to 100 already. And then regarding this attendance, once you miss just one time of a class, and then even if you achieved 100% score, but it will be just deducting your total points. So once you miss 1 class, even if you achieved 100 score, and then it will be, the total will be 99% 5 scores. Okay, and we roughly have 16 weeks, and then per 2 times per week, and about 30 class in total. And so this can be considered as taking up about 15% of your total grade or score. Okay, so once you miss the entire class, and then even if you got a perfect score, it will be around 85%. Okay. Okay, that's actually the last slide about the course introduction. So any questions? And also, although the class will be done in English, but you guys then ask the questions in Korean. Yeah, anytime. Okay, so feel free to ask anything in Korean. Any questions? 네? 좀 하죠. 좀 하죠. 합시다. 네. 네, 작년 같은 경우에, 아니 작년이래, 지난학기 같은 경우에도 약간은 내가 좀 목표하던 진도라 해야 될까? 그거를 좀 못 끝낸 경향이 좀 있었어요. 그래서 항상 그렇게 되더라고요. 나는 열심히 달리는데도 항상 좀 어쩔 수 없이 좀 느려지더라고요. 그래서 근데 마지막 기회 항상 제일 좀 핫한 거고 좀 가장 좀 인트레스팅한 부분인데, 그래서 좀 그런 아쉬움을 좀 미리 좀 예방하고자 조금 진도를 나가봅시다. 네.
교재 PDF를요. 레코드에다 줄 수 없나요?
교재를?
그러니까 잠깐 한 일주일 정도 올렸다.
네. 그거를 내가 올리면 좀 거시기 하잖아요, 내가. 네? 영세 그래도 교수인데. 네? 그래서 내가 그냥 네. 여러분들 우리가 이제 컴퓨터 사이언스 그리고 작년 이맘때, 작년 정확히 1년 전에 내가 무슨 과목 가르쳤냐? 상영어이긴 하지만 이제 정보 검색이라는 거 가르쳤다는 거예요. 인포메이션 리트리버. 정보 검색을 가르쳤는데 어떻게 이제 정보 검색을 하는지를 내가 가르쳐줄게요. 보이죠? 이야. And we just type the author name, and then Google will give you this nice autocomplete or relevant query expanded result. So this is called the query expansion. Okay, so there are two techniques that are used here. One is autocomplete. Okay, so once you type prob, P-R-O-B, and then it will automatically fill out the rest of your word. That's called the autocomplete thing. And then this thing. So even though I just type the probability and statistics and walpole, and then it actually automatically expands your query so that you can clarify your kind of information needs. Okay. So these are kind of different, like a path of your different information needs. Okay. So in this case of putting the PDF, so your information is definitely meaning that you really want the PDF, not just general kind of information about the book. Like so the book price or how many pages are there, such kind of information may not be that much relevant in your needs in this specific case, right? So that way you can clarify your information needs, and that is done via this technique called the query expansion. But anyways, yeah, so already the PDF results are coming up, and one of them is just a full textbook. Okay. Any other questions? So yeah, this nice colors slides are actually not the one that I created. So I'm kind of lazy in that sense. So I'm just using the slides that are provided by the publisher. So in the case of very, very famous books, in this case, this is probably one of the most famous books used as a textbook in this probability and statistics course. And then since it is so famous, the author or publisher is already providing these slides. So, but sometimes these slides may not make much sense. And also I may add more explanations in addition to these slides, right? In terms of what I think is really important, right? So yeah, I recommend you guys to pay attention to this class and what I will kind of explain or emphasize. Okay, and also I found in the earlier semester I found myself tending to create the exam problems from my own explanations or kind of emphases. Okay. Okay, so this is the slide, and let's go through them. Okay, so this is a data set, one example of the data set, and there are two cases. I forgot what this means, but it could be like the height of a particular vegetable or something when they were provided nitrogen or not. Okay, so we have two different cases that we want to compare and contrast, and then we can just collect those measurements that we are interested in, and then they can be visualized as a kind of dots along this horizontal line. And since we have just a one-dimensional data, so these are the two different cases. But basically, these measurements are just single numbers, and those single numbers can be represented in a single axis, right? And those circle and this X mark is representing their two different cases between this no nitrogen and nitrogen. And yeah, there are many kind of a little bit of a philosophical introductory kind of, descriptions in the book, but I don't think this is that much important. But here, briefly, the population is so you want to obtain the distribution of the heights, or maybe the average heights of man living in Korea or living in Seoul, for example. Okay, and then all the people satisfying that criteria will be our individual data item, and that will be called this a population, and they will have their kind of own underlying probabilities that we don't know yet, right? So we can think of like a histogram of 150 centimeter and 155 and 160, and then those kind of histogram will be basically our true probability. So we can consider this kind of true probability, and then we basically obtain the sample from this probability. So we will get a sample from this range with the highest probability, right? And so those kind of true probability is placed in this part, and then from this probability we get actually the sample data. So sample is basically sample, and here the important part is this is basically subset of our population. So population can be considered as really large number of data items, but in practice, in almost all situations, we only get a smaller number of subsets sampled from this entire really large population. Okay, and from the sample we can do this statistical inference. So suppose we obtained like 160, 163, and 171, and 148 centimeter. And then what will be the mean of this true distribution? Okay, and then we can simply compute our sample mean, which means the average value or mean only using our samples. Okay, so limited or small number of samples. So that way, even though that mean can be a little bit different, so it may not be exactly the same as the true value, right? Because it's only from this limited number of subsamples, but at least we can kind of guess. Okay, roughly the mean will be around. Let's see. Okay, so in this case, let's use the technique that we used in high school. So we can set up the initial average of 160, right? And then we only consider the difference, right? So it's minus 2, and 0, and 11, and 3. And then we can just compute the average, and then we add this average to this initial mean, right? So that's one way to simplify the computation, right? So it's let's see. So it's like 3. So the average should be 163, right? So this is a kind of sample mean or kind of empirical mean that we obtained, but it may not be the same as the true mean, right? But we kind of guess the true mean is 163, right? This kind of guessing process is called this inference, okay? And then since we are using the statistics, we obtain this multiple number of samples, and then we infer our mean from these samples. So that way we call that as statistical, okay? So that way, this kind of process is called a statistical inference. Okay. Yeah, so this is another data example. So we have like 2 sets of different conditions. Okay, so previously we considered only one condition, one set of condition, nitrogen or no nitrogen. But we consider 2 sets of condition, depending on this humidity level and also whether that was coated or not coated. So it's like a little piece of metal, and then if we coat that metal with the aluminum, and then it will last much longer. So it will not turn red in a short amount of time, which is bad, right? Okay, so coating is basically a better one, but we want to know how good. I mean, how much? Yeah, what amount of like benefits that we will get by additionally coating that piece of metals. Okay, that will certainly cost additional money, right? So that is actually worth doing so or not. Okay, in that kind of context, we can compare these 2 conditions of coating and uncoating. Right? So basically, depending humidity level is now 4 different levels instead of just 2. Okay, so we at one condition we have 4 different conditions, and another set of conditions we only have 2. Right? So they are all like a crust, right? So that way, like these. We have 2 different conditions, right? And so these 2 conditions are duplicated. So we now have 4 different cases, and these are the sample numbers, or these are the measurements that we have or obtain. So we are basically interested in average corrosion times. Okay, so how long it will last. Okay, so those time measurements are like collected in those numbers. Okay, then these are kind of means. Okay, so I briefly mentioned about the statistical inference, and then I mentioned about the mean, or more exactly sample mean. But as we already know, so there are another kind of measures that we are quite familiar with called variance, right? So we are interested in the mean and also the variance, right? And then there are many other measures. So the mean is kind of a first order statistics, and the variance is called the second order statistic. And then we can think of third and fourth order statistics. Okay. But anyways, so this is a definition of the sample mean, right? So we have a measurement, and then we have the total numbers. Okay. And let's just focus on this definition, the notation. So usually the sample mean is by just taking the bar on top of this letter. Okay. In that case, usually we think of it as a kind of sample mean. And then here, this is called sample median. Okay, sample median. So you guys know what the median is? 그죠? 한국말로 중간값이죠. Okay. And then, so there is 2 different definitions here as we see. So if our observation or the number of samples are odd number, and then there is clearly like the median item. So -1, 1, 5, 7, 8. And then this one is clearly our median in the middle, right? When they are sorted out. But what if we have another data like this? Okay, so in this case, there is no clear median, right? Because, yeah, so in this case, we just consider, or we just promised, or we kind of agreed that our median in this case is just the average between these two values in the middle, okay? So that is a mathematical representation of this, okay? And this kind of a median and a mean has like a little bit of practical meanings, or they have different behaviors. So in the context of machine learning or artificial intelligence, there are some classes of methods called a robust something. So you guys you guys have probably heard about the deep learning, right? But suppose you invented another new type of deep learning, and then you named it, or you gave a name of it as a robust deep learning, okay? And then without looking at all the details, we now should be able to get a brief idea about how it will kind of work, okay? So let me describe let me describe what that is. So in this case, let's use just a simpler case of this guy. So this is a clearly mean, and then the median, and then what is the mean? Oh, okay. And also one thing is that the median is using this kind of notation, using tilde. Okay. So here, mean and median. Median is definitely 5. And then what is the mean? Mean? How? 4, right? Okay. And then suppose these measures, or these values were kind of measures by some electronic devices, something like an oscilloscope or some other kind of measurement by some hardware or some device. But somehow this device kind of malfunctioned, or someone actually intentionally changed some of your data. Okay, so for example, I changed this value, or some faulty device actually made a mistake of measuring this value as 8,000. Okay, so this is just clearly a mistake, and this is clearly a wrong value, right? But in this case, this one will definitely change, or the sample mean will definitely change, but this median will still remain the same, right? So that way, so these types of values is called outlier. Okay, outlier, and then this median is not influenced at all by those outliers, right? Although, if you change these 3 values, okay, so this guy as 7,000 and this guy as 5,000, and then your median will no longer work, right? So in this case, median will be also influenced in a bad way, right? But if we assume that those faulty values are really a minor portions out of your entire data, then your median value will remain the same. So that way, your measure is robust against those outliers. Okay, so that way, we call that as a robust something. Okay, so in the case of back to the deep learning that you might be interested in. So if someone is calling our method as a robust deep learning, and then they will probably use something related to this kind of median thing. Okay, and then those median is really playing an important role. But in general, for example, deep learning using this mean value is computed much faster. But if you use this median one, and then the computation or the training time or computing time that you have to run your program about the deep learning will take much longer. Okay, so that's kind of downside of this robust methods. Okay, so yeah, related to this deep learning, and yeah, who will ever this intentional manipulation of your data, right? So who will kind of make your data wrong? Okay, so yeah, so if we imagine what situation will be corresponding to this type of like case, and then there are actually many cases related to kind of security. Okay. Okay. Just to interest you guys, let me just show you one example. So this is really hot topic in these days. Adversarial networks or machine learning. Okay. Yeah. So this guy, Ian Goodfellow, and many other folks are working on this topic. I mean, many other folks in DeepMind in the UK, they are doing the research. A lot of research in that. Let's see. Let me see if I can find one example. Let me see. I'm looking for school bus. Yep. Let's see. So this is one example. So this guy is clearly school bus, right? But the second picture is kind of additional noise that you add to this school bus, okay? And then overall, the third picture, this guy, it still looks the school bus, right? But your deep learning or neural net, until this, I mean, for this, deep learning said that this is okay, I think it's a school bus. But in this case, by just adding a little bit, just a slight noise, which looks still as a school bus, but your deep learning or your neural model will suddenly tell, oh, okay, that is a dog, or that is dog. So I'm completely sure, or I'm entirely sure that this is a dog. Okay. So this type of behavior, which is not desirable, is actually happening in the world of deep learning. So if you're gonna intentionally mess up your model, and then this can be really a serious problem. So if you imagine you are riding a autonomous driving car, okay, and then it will probably recognize all the objects. Okay, there is a person there, and this is a road which is going straight. And then this is a sky, and this is a traffic light, and so on. Okay, and traffic light is currently like a red color, right? And so the car stopped, but suddenly someone hacked your system and then added a little bit of noise like that there, and then suddenly your car will hit the person and kill them. Okay, so that is actually, that might really. Okay. So this is a sample mean. And then this is a sample variance. So you guys know how to compute the sample variance. So suppose we have like 3 data. Let's see. Of 1, 3, and 5. And then what is the mean? What is the mean? 3. And then what is the variance? Where is the variance? 4 squared and 0 and this, right? So this is our sample variance. Is it true? Is it right? Right? Yeah, this is what we computed until the high school, right? But really, in the correct way of computing this variance, is that instead of dividing by the total number of samples, we actually divide the total number of samples minus 1. So that's what this means. Okay? So we now, from now on, we actually compute our variance, or this sample variance, because the reason for calling that as sample variance, not just a variance. So we now consider like two types of variance. One, which is a true variance, which we don't know yet, right? And also we have a sample variance that is like computed based on our limited number of samples, right? So that is the meaning of this sample variance. And then the sample variance will now have the denominator of n minus 1. Okay, so I think we will have another chance. Another opportunity later in this class, later in this semester, about why this should be true. But in this case, it's like, okay. So in this case, like 4 squared is 16, and 32 by 3 versus 32 by 2, right? So I'm saying this one is a kind of a correct way, right? So this is our previous way, right? Which variance is bigger? Which variance is bigger? The right one, right? And so we actually, previously we actually underestimated our variance, okay, compared to the true variance. So in this case, the variance is estimated or inferred as a larger value than we used to know, okay? And so, so let me give a brief reason about why, okay? So, when computing this variance, our initial assumption is that we know the true mean, right? So we need mean to compute the variance. Again, in order to compute the variance, we need what the mean value is, right? But in practice, we don't know the true mean, right? So also in the case of mean, there is a true variance that we don't know, and then also we have a kind of sample mean, right? So in practice, we don't know the true mean, but we know this sample mean, right? Which is not actually the same as the true mean, right? So this guy is actually doing something in estimating this sample variance. So if we were to replace this part as our true mean, and then in order to correctly estimate the variance, we have to divide them by n, okay? But since we are using this sample mean, which is not exact, we have to use n minus 1, okay? So let me just give a little bit more explanation about why at a high level, okay? So suppose your true mean was like 3, okay? And then so this is a true mean. But unfortunately, you obtained the 3 sample, and then your sample was unfortunately higher than this value in general. For example, 4, 5, and 3, okay? So in this case, this is your sample. In this case, the sample mean will be, of course, 4, right? But what about the variance? In order to compute the variance, if you were to know this, the true mean, and then it should be something like this, right? But unfortunately, your sample was giving you the sample mean as a higher than your true mean, okay? So in this case, 4 minus 4, okay? 5 minus 4 plus 3 minus 4, okay? So this will be what you will compute by using the sample mean instead of the true mean. So if you compare these two values, this value will be much higher. So this value should be your correct way of variance, but you don't know the true mean, right? So this way of computing the variance will naturally give you a smaller value, okay? So since it will give you the smaller value, instead of dividing by n, we have to divide by n minus 1. Okay? Although you might still have a question, why not just using n minus 2 or n minus 3 or so, and so on? But it's it's actually related to something called degrees of freedom. Okay, so degrees of freedom, which I don't know clearly yet. But yeah, we will learn more about it later in this course. Okay. Okay, and then sample standard deviation is just simply just a square root version of just a sample mean. Okay. Okay, and then discrete and continuous data. So you guys know what the discrete variable and continuous variable, right? So for example, let's consider the blood type A, B, AB, and O. Are these values discrete or continuous? Discrete one, right? But what about the height? Height can be any values in kind of real value, although it can be like a 2 meter or 3 meter or and so on. I mean, in practice for a person's height, right? But they are actually definitely like residing or existing in a real value domain, right? So they can be like 164.3751 and so on, right? So those values can be really like infinitely different numbers, right? So all the possible numbers can be an infinite number. So in that case, we call that as continuous variable or continuous data, right? But in practice, as we collect all the various types of data, and then some of them will be discrete, and then some of them are continuous. Okay. Okay, so this is another example that we have no idea about, right? So tensile strengths. I don't know what that means, but yeah, I actually know because I read the book already. But it's like, yeah. So let me explain this. So suppose you are running a company that makes clothes. Okay, so nearby there are Dongdaemun shops, right? So they are selling all the different kinds of clothes, right? And each clothes will have their different mixture of different chemical components, right? And then like a 100 cotton and then like 20% polyester and so on, right? And so suppose cotton is a little bit expensive, right? So in order to create this clothes, suppose this is the portion of the cotton in our clothes, and then the resulting kind of a measure that we are interested in is how resilient or how durable our clothes is. Okay. So this is like a duration or strength of your clothes. Okay, so if we use less cotton, and then it will last like a less force. Okay, it will hold a less force. And so these are the measurements. So for this cotton percentage, we obtained like 5 different samples and so on. Okay. So we can of course represent these data in this form of a scatter plot. Okay, so we assign these 2 axes, where the first axis is telling us the cotton percentage, and then the other is tensile strength. Okay, and this is called a scatter plot because we are scattering all the data points as a dot, and dot is representing each of your data items. Okay, so that way we call it as scatter plot because you are scattering all the different points. Okay, just to interest you again. So there is a very, very famous method to generate this scatter plot in a much more interesting way. So that is called this T-SNE. So this is a quite the state-of-the-art machine learning and artificial intelligence method. And actually, I do a lot of research on related to this method. But anyways, in terms of an output that we will get, okay, view image. So this is even interactive, although this is just a static screenshot, but it's made as an interactive version from the Python or if you're familiar with the IPython notebook, and then it will create like an interactive version of this plot. But anyways, this is also called a scatter plot. Although here, in this case, x and y axis doesn't have a specific or explicit meaning. Even though in the previous case, the x was a quotient, like a percentage, and the other was tensile strength. But in this case, it's kind of tricky to define what the axis means. Okay. But anyways, so these are kind of example of the subreddit documents. The subreddit is, so it can be thought of as kind of a Twitter. Basically, it's a social network, like a bulletin board or something. But it has all the different, it can be viewed as, you can consider it as a neighbor cafe, okay? And then they have all the different topics, right? And then each cafe will represent different topics, and then each cafe will have their own sets of documents that people post, right? And then each document posted in different cafe will be represented now as a single dot, okay? And then if they are closed in this 2D scatter plot, I mean it's basically a 2D, right? So it's called the 2D scatter plot. So in this scatter plot, if the two dots corresponding to two documents are close to each other in this scatter plot, and then it means they have the similar meaning or semantic contents. So in this case, roughly in this region, those documents are all related to like programming. So probably those documents were collected from Stack Overflow and something like that. And then on the other hand, these top documents, which are still represented as dot, they are all related to the gaming topics. Okay. So that way we can kind of view the overall kind of relationship between different topics in terms of how much they are different and similar to each other. Okay. So for example, so in order to understand what's going on or what happens in this deep learning, so suppose you, one of the basic basic usage is something like this, okay? Okay, then this is a car battery life. Yeah, so we have a bunch of measurements. And then there's something called this stem and leaf plot. And this is really simple one. I just learned it last night. And so what this means is that, so suppose you have these amounts of data, and then you collect all the first digits. Okay, so first digit will be 2, 4, 3, 4, 3, 3, 3, 2, and so on. And then it's basically binning, or you can just imagine it as a histogram. Okay, and so you collect all the measurement that starts with 1. Okay, and that's called the stem. And then this leaf is the second number after the digit, after this digit point. Okay, so this means, so this means Bluetooth got died. See, I'm gonna turn off the Wi-Fi. Okay, come on. Give me just 1 second. Okay, so in this case, it means we have 1.6 and 1.9. Okay, and then no other data that starts with 1 something. Okay, so that way we can collect those data that starts with 1 dot and 2 dot and so on. And then we consider this double stem and leaf. Okay, so that is like we kind of split further. So in this case, suppose we had 1.1, 1.2, 1.4, and 1.6, 1.7, and 1.9. Okay, and then this is actually like collecting all these data into one bin, right? It would have just this one row, but this is 2 cores, and then we can split them further into this range as 1.0 to 1.4 and 1.5 and 1.9. Okay, So we can have these two ranges. And so here 2 star is corresponding to this. So in this case 2.0 and 2.4, and this is 2.5 and 2.9. Okay, so that way we only see 2 and we only see like more than or greater than or equal to 5. And these are the frequency. Okay, so that is called double stem and leaf. Okay, so relative frequency distribution. It's basically frequency. It's like a binning with the equal interval. And then these are the total frequency corresponding to each beam, and these are the median value of this class interval. And then they can be graphically shown as this histogram that we are quite familiar with, right? So that is the histogram, and also this thing is, so you can imagine this guy as our true distribution, true probability distribution or density that we want to find out. Okay, and then this histogram is the estimated probability distribution that we obtained from our sample. Okay, so basically, if our sample gets larger and larger, and then these histogram will be more and more become more and more similar to this true distribution. Right? So there is some law that corresponds to this behavior. Does anyone know what the name of that law? The law. Yeah, there is something called WLLN. Is it right? Yeah, not sure, but the large number of laws, law of large number. So weak law of large number and strong law of large number. Okay, so it means, so whether you say weak or strong, the main message in this law is that once you obtain more and more sample, okay, and then whatever you do, like obtaining like sample mean, sample variance, or mimicking this probability distribution, all these estimation or inference will become close to your true answer. Okay, so that is the main message of this law of large number. So basically, large number is the king. Large number of sample. Okay, and there is a skewness. Skewness is like about the symmetry. So suppose this is a probability distribution. So this is symmetric, which is not skewed at all. And then in this case, suppose this is about the mean, but the probability is definitely skewed to the left. Okay. So in this case, suppose I'm gonna say I'm gonna tell you like on average, the women's average height is 160. Okay. But in practice, I mean, the skewness is saying that, okay, if it's a left skewed, and then when you have just one sample, you need a new girlfriend. And then, on average, the height will be 160, but it's more likely that your girlfriend will be shorter than 160. Okay. Yeah, let's use this guy. Okay. Okay. Your girlfriend will be taller than 160 in this case of a skewed probability distribution. Okay. Okay, this is a box plot. Okay, so let me finish it within 10 minutes. Okay, so I just want to finish this chapter 1, and there are not much left here. Okay, and okay, I'm gonna promise you that I'm gonna finish it before 1:30. Okay, so please bear with me a little bit more. So this is called a box plot. Okay, so this is a more richer representation of your distribution. So this is box, and this guy we have a line here, and then we have this kind of a box width, right? Does anyone know what these mean? So first of all, this value, and this value. Does anyone know? Bonus point. 여기야. 네, median. 이거는 네, 75% 25% 그죠? Okay. So here, yeah, you got a bonus point. Yeah. So this line is representing your median. Okay. So you imagine, so you obtained your sample and then you sorted them out, and then your number of sample is 100 different sample, and you sorted them out. Okay. And then you obtain the median value, and then that median is visualized as this line, and then this guy and this guy is like 25th ranked one and 75th ranked one. Okay, so you can imagine like, so suppose we have 100 students here. Okay, at the after taking a midterm exam, the highest score was like 100, hopefully, and the lowest score was like 45. Okay, and then we can rank or sort all of your scores, right? And then you pick up the 25th ranked students score and 75th ranked score, okay, and that value is called 25% or first quartile, and this is a third quartile. Okay, so quartile means quad is 4, you know, like quad core, i7 and so on, right? Quad means 4. And so here we divide your data into 4 pieces. So that's why we call that as quartile. And the first quartile is the top 25th, and then the third quartile is actually the 75th ranked, right? So that way we call that as first and the third. And this is the second quartile if we call that way, okay? Okay, and then these values. Oh, okay. So this range is called IQR. So interquartile range. Okay, interquartile. Inter means like in the middle. Okay. So that way we call that as IQR. IQR. I don't know how much is important, but that's what this book says. But anyways, and this line. So there are different strategies to determine this line. Okay, but usually it's like, yeah, if you think about this quartile or this kind of ranked thing, you can imagine like a 9th ranked student or 9th ranked score, and also 91st ranked score. Okay, so that's like a 9% quartile or 9th ranked or 91 ranked, and then we will have 9 remaining kind of outsiders who are really good at this class, or also another 9 students that did really poor, unfortunately, in this class. Okay, so we can represent those as these dots. Okay, so those really need a special attention. Right? So they might like kill someone else, and they might really like win a Nobel Prize in the future. So we have to have a really special treatment of them. Anyways, this is just a joke, but those data items really outside or who does not follow the like a typical range of the data, so we represent them separately as dots. Okay, so that's main intuition of this box plot. Okay, so that was box plot. And suddenly, that's it for today. Okay, so before ending the class, any questions? Okay, yeah, and then see you this Wednesday.